Hello, we are the 5E22 Terabytes on a presentation of two basic line followers. We are doing EV3 tutorials and this is our very first tutorial. This tutorial will be about line followers. First of all, what is a line follower? A line follower is a program that helps robots such as the EV3 or NXT LEGO robots to follow a line using just a color sensor and a driving robot. It is used in competitions such as the widely known First LEGO League, where it helps the robot to keep it consistent in its programs. We'll be looking at two types of line followers today. The first type of line follower we will be looking at is the 3-switch, and the second type of line follower we will be looking at is the proportional. Let's look at the 3-switch line follower program first. I'll explain its properties. 1. The 3-switch has 3 possible outputs for any light sensor output. 2. If the light intensity provides a higher than target value, which is too white or bright, and is too far to the left, it turns white towards the target path. 3. If the light sensor value provides a lower than target value, too dark or too far to the right, it turns left towards the target path. 4. If the light sensor value is equal to the target value, the robot's light value is completely on target, and the robot will continue to drive straight on the line. Here is our line that we are following. These paths represent the possible light sensor values the light sensor could be detecting. The blue line represents the situation that the reflected light is too high or bright, which is too far to the left of the line. The pink line represents the situation that the reflected light is too low or dark, which is too far to the right of the line. Finally, the orange line represents the target path. If the robot is detecting the same value as the path's value, the robot is on target and is correctly following the line. These are all the possible inputs in the 3-switch program. The robot has 3 possible output actions based on the 3 inputs. If the measured light value is too high or too light, it turns right to correct, since it is too far left. If measured light value is too low or too dark, it turns left to correct, since it is too far right. If measured light value is equal to target, it goes straight, since it is already following the correct path. Let's see the math behind this. Let LSV be the light sensor value and the ROD in degrees be the robot's output direction based on the LSV. Using these variables, let's construct a graph to illustrate all the possible actions of the 3-switches code. Here is the graph. The dots represent gaps in the lines where LSV is larger than 0 and LSV is smaller than 0. Why? Let's say where LSV is equal to 0, the light sensor value is really equal to the target path. So, our target is that the LSV is quote-unquote equal to 0 for just this graph, when our target in reality is that LSV is in the middle of the black and the white lines. That explains the dot I just put in the middle. Taking what I just said, when the light sensor value is equal to 0, we are on target. So when the LSV is equal to 0, or actually the target value, the robot's output direction is 0, since 0 is moving forward on a degree scale. On this line, light sensor value is larger than the target value. The light sensor value is detecting a light sensor value too high. To correct this, any light sensor value where LSV is larger than the target value, the robot's output direction is moving at a positive direction. This makes the robot turn right from the left white line, because the positive direction on the degree scale turns right. On the line LSV is smaller than the target value, the light sensor value is detecting an LSV too low, meaning the robot is too far right on the black line. Any value where the LSV is smaller than the target value, the robot's output direction moves in a negative direction on the degree scale, so it turns left to correct. Now that we've got the maths done, let's see the program. Okay, here is our 3-switch line follower program. The first step is to put in the loop. As any other line follower, we need to put in a loop to repeat the actions of the line follower over and over again. If I could just get this loop together, thank you. Okay, we're gonna set this loop for forever. Normally in competitions, this loop will only be set to a condition, but since this is just an example program. We'll keep it at set for forever. Then the next step is to test first whether the light sensor value is less than the target value, as it says in the pseudocode here. We use a switch to determine this. Okay, if this switch's statement is true, whatever happens in this box will happen. But if the statement is false, whatever is coded in this box will happen. Then the next step is to condition this switch. We set it to color sensor, compare, and reflected light intensity. Then we need to set it to test whether the light sensor is less than the target value. Our target value is 40. Yours will be different, so this is how you get your target value. To test your target value, you need to put your color sensor in between the black and white lines that you are following, and use the port view to see what the current light sensor value is. Whatever that light sensor value is, you use that as your target value. Okay, back to the program. If this switch is true, the robot is detecting a light sensor value is too dark, meaning it is too far right on the black side, going back to the line. So we have to turn it left. And to turn it left, we have to take a steering block, set it to the correct ports. Our ports is for our motors is port A and B. Set it for on. Set it to our desired speed and move it in a negative direction, since the negative direction turns it left. Then, if this switch is not true, there are only two other possibilities. The light sensor value is either larger than the target value, or the light sensor value is equal to the target value. We separate these in the false section of our first switch, over here, since this only comes into action if the light sensor value is not less than the target value. To separate these, we test using another switch if the light sensor value is larger than the target value in this false section. If this is true, then the light sensor value is larger than the target value. But if it is false, then we can deduce that the light sensor value is equal to the target value. So we set this once again, to color sensor, compare, reflected light intensity. And we condition this to test if the reflected light intensity is greater than the target value. Our target value again is 40, yours might be different. And if this second switch's statement is true, which is light sensor value is larger than target value, then our robot is detecting a light sensor value too high or right, meaning our robot is too far left on the white line. So we need to turn it right to correct. Same as before, we take the steering block, put it in the true section, set it to on, put in the correct ports, set it to our desired speed, and finally, instead of putting in a negative direction, since a negative direction turns it left, we turn it right by putting in a positive number. And since we want to balance this program entirely, we need to do the opposite direction of the negative direction we put in our previous steering block. Our previous steering block, we put in a direction of negative 24, so in here, we need to put a direction of positive 24. Then, finally, if the light sensor value is not less than the target value and not larger than the target value, then we know that the light sensor value is equal to the target value. If it's equal to the target value, we need it to drive forward. To drive it forward, we put our final steering block in, set the final ports back in, you know the rest of it, desired speed, and leave it at the 0, since a direction of 0 on a degree scale is moving forward. And that's it. Now we can move on to the proportional line follower. Here are our proportional line follower properties. 1. The proportional line follower turns according to the measured reflected light intensity and turns more the further away from the target path it is, making it very stable. The proportion, or the ratio, of the difference of the light intensity to the direction output can be changed to alter the sharpness or amount of correction the robot acts out to follow the line. This is where the name proportional comes from. So what does the proportional line follower actually do? Here are the steps of the proportional line follower. 1. The robot measures how far away from the line it is. 2. The robot takes the value and proportionates it. Is that even a word? I don't know. And proportionates it to smoothen its corrections. 3. The robot takes the final value and plugs it into the robot's direction of movement. Let's expand these steps a bit. 1. The robot measures how far away from the line it is. So, instead of using the function of comparing the values, we measure the values. First, the robot measures its current reflected light intensity. Let's say it's too far left on the white line and is measuring a reflected light intensity of 90. The robot then subtracts the target value of, let's say, 40 from the current light sensor value. The output number is called the error. So the error, which is 50 in this case, is the percentage difference of reflected light intensity from the target value, or the distance from the target path. So, step 1 complete. 2. The robot takes the value, now known as the error, and proportionates it to smoothen its corrections. Before we begin this step, we need to know what proportionality is in this context. The proportion is, in this context, the ratio from the input error to the output correction, with the proportional constant being a variable of your choice. Take it this way. The robot is using the program, but the robot is making sharp corrections, too sharp, and isn't going accurately straight. To reduce the amount of correction and smoothen the robot's movement, we need to reduce the proportion of the robot's error to correction. So, for the same amount of error, the one with the smaller proportion has a smaller correction and therefore a smoother path. On the other hand, your robot might take too long to correct and never get accurately close to the line. In this case, we need increased proportion. My point is that there's an optimal proportion that is neither too high or too low, and you need to find that for yourself. And of course, we'll plug the final value into the robot's direction of movement, but more on that in the programming later. Once again, let me illustrate the math behind this with a graph. Let's show the line after step 1. This is the line that would have happened if we followed the line by step 1. For every percentage of error increased, 1 degree of the robot's direction is increased. However, we can fine-tune these values by adding the proportional variable. Before step 2, the error would be equal to correction. After step 2, the error multiplied by the proportion would be the amount of correction used. Any of these colored lines could be the amount of correction used. With less proportion for the same amount of error, less correction is used. With higher proportion for the same amount of error, more correction is used. The proportion, or K, could be any number, but you're going to have to test and decide that for yourself. Finally, let's see the program. Okay, here is our proportional line follower. Our first step is to set up the two variables that we need to use later in the program, which is the proportional constant, which is Kp, and the error variable. As you can see, I already made mine, but to create yours, you're going to have to press the title at the top and press the add variable and name it the Kp and error. So we're going to put both of the variables here. Again, remember that your robot you need to fine-tune your own robot to the correct proportional constant. But for our robot will be tuned to 0.5 for its proportional constant. Then the next step, which is the same with any other line follower, is to put in the loop. Again, you're going to have to condition this if you're in a competition of some sort, but this is set for infinity for just this code, because this is an example program, as I said before. Sorry for my stutter. Okay, the very first step inside the loop is to measure how far away we are from the target path. To do that, as before, we need to take our measured reflected light intensity by putting in a color sensor block, setting it to measure reflected light intensity. And then we need to take away the target value by putting in a math block, plugging the measured reflected light intensity into the first parameter, setting it to subtract, and subtract the target path value from it. Again, your one will be different because you have a different robot, but this is our target value for now. This output is whatever the error is going to be. So to put this into the error, we take our error variable again, and set it to error, and then plug the values from the first math block into the error variable. This will store the value of the error into the error variable so we can use it on it later in the program. As you can see, I'm going to use it immediately after in the program, but if you're going to extend the line follower to make it more advanced, it's a very good choice to plug it into some sort of variable to store it for later on. So, like I just said, we're going to take our KP and our error variables, because we're going to have to multiply it to proportionate the error. After we proportionate the error, whatever the output will be of this second math block will be the robot's output direction that we want to use to steer the robot. So, to multiply these two values to proportionate the error, we set it to read numeric, so we can set the stored values inside as an output so we can use them in the math block. So we put them both into both of the parameters of the math block, like so. It doesn't matter what order you put in as long as they're in both of the parameters and you set it to multiply, because either way they would be multiplying by each other. And of course, our last step is to get the steering block, turn it on for on, you know the rest, set it for our desired speed, and finally plug the robot's output direction into the steering block here. And that's it. That's the whole proportional line follower. Thanks for watching, and I hope you enjoyed our video.